Good afternoon, everybody. Last time we introduced vectors and we worked with them, and I believe I ended by promising you that we would look at how one can multiply vectors together. So there's really two different ways, at least two different ways of doing this. The first is the dot product. And so let's define it for three-dimensional vectors. So I have a vector A with its component form and then B in component form. And the dot product of A and B is a scalar, actually. So we're going to dot these two vectors and we get out a scalar. We denote the scalar by A and then a big dot B. So the dot product is A dot B, and it's equal to, well, you multiply the first component of A times the first component of B. So A1, B1 plus second component, A2, B2 plus, you got the idea now, A3, B3. So that's it. It's a very simple algebraic operation. There shouldn't be much difficulty for you to compute these. Of course, there's more to the story always, but strictly computing these is not too bad. So the dot product for two-dimensional vectors holds exactly the way that you think it should. You just don't do the third component. So here, let's work this one out. The dot product here would be what? Well, it would be 2 times 7 is 14, plus, if you want, 5 times minus 1, and you end up with 9. The dot product here, if you want to rewrite them in component form, you can, or you can think through it. The first component for this vector here, let's switch to component form. This is really 1, 2, negative 1, dot 0, 2, 2. And let's see, well, you get a 0 from the first component, 0 times 1, a 4 from the second component, and a negative 2. So we should end up with a 2. So the dot product here is 2. And so I do want to point out to you just a simple question that one might ask, and that is, what happens if you dot a vector with itself? And let's go ahead and work over the three-dimensional case. It doesn't really matter. But if we work over the three-dimensional case and I look at A dot A, I hopefully easily see that dot A is, well, it's A1 times A1, so A1 squared, plus A2 times A2, so A2 squared, plus A3 squared. And we've seen that number before. Where have we seen it before? Well, we saw that what? I'm going to write it in red and then just erase it. The length of A, we saw, was the square root of this expression, right? This expression right here. And so the point is, if you were to square the length of A, then you'd have exactly what we have. This A dot A is exactly the length of A squared. And so that's a really handy little fact to keep in mind. Okay, so I wanted to run through some basic properties of the dot product with you. Nothing too fancy here. We just learned that A dot A is the length of A squared. If you take a dot product and you want to dot it with the sum of two vectors, it distributes in exactly the way that you really would expect it to. So you get A dot B plus A dot C. And somehow this may seem obvious to you, and it should, because it's familiar and expected, but these things aren't necessarily true. It doesn't have to be this way. And so this has been checked and shown to always hold. 0 dot A, you would expect that to be 0, and it turns out that it is. Now think carefully. Is it the 0 vector or is it the 0 scalar? Well, the dot product gives you a vector, a scalar, so 0 dot A is the 0 scalar. A dot B is the same as B dot A. It's not too difficult to see that when you look at the formula for the dot product. And finally, what if there's a little scalar? What if we're scaling A and we dot that with B? Well, that's actually the same thing as C times A dot B. And you can even, if you want to, slip the C over here times B. Now, I forgot to squeeze the dot in, so let me adjust that. Hopefully we can, yeah, there we go. It's A dot and then CB. So you can put the C either with the B, with the A, or just times the whole thing here. All right, so let's break this video here, and in the next video we're going to ask ourselves what the dot product means geometrically.